So what do you expect to happen to the dissolved oxygen in here? Up, down, stay the same.
Down.
Down. Right. Makes sense, right? There is no oxygen production. From our initial reading, there is no oxygen production because the lights are turned off, and there will only be oxygen consumption. So again, just to make things easy, let's say tomorrow we read this and we get 1 part per million. And that's because this was going on. C6, C12. All right. Okay, now the question is, what do we do with these numbers? How do we use this light and dark bottle information to figure out what productivity is? Well, the first thing we have to do is we have to figure out what represents respiration here. Well, that's pretty simple. If we take the initial reading and subtract the dark reading, that should be respiration, right? That number should represent the amount of oxygen consumed in respiration. So respiration should be equal to the initial bottle minus the dark, and that's going to be 10 minus 1 equals 9. So we would know then that 9 parts per million of oxygen were used up in 24 hours in respiration. Now the question is, well, how much oxygen was produced? How do we figure out, using these 3 bottles, how much oxygen was produced? Well, this kind of looks like we might use something here. If we started with 10 and ended up with 100, that looks pretty good. That's oxygen produced, right? So what do we do with those numbers, the 100 and the 10? We add them, multiply, divide, take the square root, subtract. What do we do? Kayla, what do you think?
Subtract light minus initial.
Okay, good, very good. So light minus initial would tell us how much oxygen we gained, right? Make sense, everybody? All right. But there's a problem with that. Because wasn't there respiration going on in this bottle too? Wasn't there just as much respiration in here as in here? And so really, there was more photosynthesis going on than is represented here, right? Because all the oxygen that was used up by respiration was also being produced by this time. It doesn't show up anymore. So what else do we have to do? How do we throw in the amount of oxygen that was used up in respiration? Pardon me? Yeah, okay, so we have to add the initial minus dark. Does that make sense? We take the amount that was left over. This not only represents 100 minus 10 not only represents the amount of photosynthesis went on, it just represents the amount that was left over after we took out the amount we needed for respiration. So we have to add that respiration amount back to it. And this tells us then this is going to give us our gross productivity. Gross productivity is going to be light minus initial plus initial minus dark. And so if we plug in our numbers, we get 100 minus 10, which is 90. And we're going to add to that our 9 That's the gross productivity. All right, net productivity then, that is, how much was there available for new plant growth? Net productivity is just going to be our gross productivity. I'll put a formula here, just gross minus respiration, which is going to be 99 minus 9 equals 90 parts per million. And that then finally tells us how much productivity there was, how much new productivity we had in.
What did you say net productivity was?
Net productivity is how much we have left over to actually make some new stuff with. Yeah, Kelsey.
Isn't that the same thing as light minus initial?
Yeah, and so there are some, here we go. There are some formulas here that we can substitute, all right? And let's go through a couple of them. I gave it this way because it seems to be the easy, to me, thinking it through is the easiest way. But this can actually be reduced to another formula, which I'll write in red. L minus D. This number is the same as light minus dark. So in the end, when you do your calculations, you don't actually have to go through all this. You can just take light minus dark. Numerically, it's going to give you the same number. And then this one is just light minus initial. Okay. Now there are some other calculations we can do. We can take this net productivity and we can actually put it into a formula for determining if the lake is going to become eutrophic or not. There's actually kind of a break-even point where when the lake has a certain amount of productivity, it's becoming eutrophic. And I will give you that number a little bit later. I'm going to go any further with it today because we've got some other things we have to get done today. But anyway, this is basically what we're going to do. So the setup for our lab will be this. We will be using...
Dan, it's probably your
stuff. It's the hydroponics behind you.
I'll tell Zach how we're doing this too. All right, so what we're going to use is a bottle like this, two of them, one for light, one for dark. What about the initial one? We don't really need a third bottle for the initial. We're just going to be using the same water in these as we tested the initial with. So we can just scoop out a big bucket of water and that can be the initial for reading. In fact, we can just take one reading for the whole class because it should be the same for everybody. We're all going to use the same water. Then we'll fill one of these all the way to the tippy top because we don't want any air in there. We don't want any oxygen diffusing in or out. So fill it all the way to the top, put a cork in there nice and tight, and that'll be our light bottle. Take another bottle, do the same thing, fill it right to the top, put a cork in, and then we're going to tightly wrap this one with aluminum foil so no light can get in. And we'll set them side by side. So all the other conditions will be the same. The temperature will be the same and whatever else it is will be the same. And then 24 hours later, we just stick our probe in there. I hope that probe fits in these.
Probe.
Perfect.
You've been probed.
And we will get our numbers. All right? It's as simple as that. Doing the lab is very, very simple. I haven't decided yet if everybody's going to do a light and a dark, or if half the class will do a light and half the class a dark. The problem with everybody doing one is, number one, that's an awful lot of measuring the next day. And secondly, I don't know if we have enough bottles. So I think what we'll probably do is divide the class in half do light bottle, half do dark. There are some things you have to watch out for, though. First of all, what's the main way that oxygen gets introduced into water? We talked about it yesterday. Turbulence. So if you take this bottle and just hold it in. We're going to have an aquarium actually, and if you just hold it in there, go blub, 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 you're going to be adding an awful lot of oxygen to it, aren't you? So if we take our initial reading right in the aquarium, and then you go blubbing water in here, you're gonna have a false reading. So what you need to do is carefully dip this in and let the water run in slowly without adding any oxygen to it. So that's the main thing you have to watch out for. We when I was working on some biology classes, I took some classes one year up on Beaver Island. Central Michigan University has a biological station on Beaver Island up in Lake Michigan. I spent the summer there, and one of the things we had to do was a 24-hour study of some lakes. We would have to go to the same spot in the lake. These are just little lakes. You go out there with a rowboat, and they were just little lakes, and you go out there and take a reading, a dissolved oxygen reading, every hour, on the hour, 24 hours, which was kind of fun. In the middle of the night, you go rowing out there every hour to the middle of the lake. We had a buoy set up there, and you get your dissolved oxygen every hour. But one thing you had to watch out for was, as you were rowing up to it, you want to make sure you didn't stir up the water too much with your oars, because you would be adding oxygen to it. So it was a fun place. The university had, I don't know if anybody been to Beaver Island? No? Okay. There's not a lot of, there's houses there and cottages, but there's a lot of vacant land and state-owned land, and nice little lakes dotted through the forest out there. And the university had some rowboats there, some aluminum rowboats that they would let us use for either research, or at night we could just go fishing or whatever. My wife went out one night with me after supper. We were just going to go do a little fishing on one of the lakes, and we had two little boys with us. And the rowboats were always stored upside down. Again, they were aluminum boats with aluminum seats in them. They were always stored upside down. We got in the boat, turned it right side up, got in the water, and I'm rowing away, and my wife's sitting back there with two little boys on either side of her. And all of a sudden, snakes started coming out from underneath the back seat, because there were so many snakes on that island. And 5 or 6 snakes just came out.
How old were the boys?
I said to them, they were like 3 and 4 years old.
Did they scream?
Yeah, well, I just said, I saw these snakes coming out, and I had no idea what to do, because I thought, I don't want to spook everybody or we'll tip this thing over, so I just said to my wife, just sit still, don't move. And, of course, she's wondering why, what's going on. There's snakes coming out. So they all froze, and I just went over and grabbed the snakes and threw them all over the place. There's a lot of snakes out there.
What kind of snakes?
Steve
They're
Irwin.
garter
That's some
snakes.
Steve Irwin stuff right
Yeah,
there.
right.
Oh, look at the snakes. Look at the snakes.
All right.
Look at the venom on my glasses.
What we need to do today is go over your review sheets. Kaylee, you might want to leave